In this video, we're going to learn how to solve homogeneous linear differential equations with constant coefficients. We'll start by looking at the general form of these equations and talk about the characteristic equation and the three different types of solutions that you can have. We'll then walk through steps that you can follow and then work through many examples so that you can see how each case is handled step by step. Let's get started. The general form of a second-order linear homogeneous equation with constant coefficients looks like this. It's ay double prime plus by prime plus cy is equal to 0. The solution to this equation is going to be of the form y is equal to e raised to the mx. To solve this equation, we're going to take that solution and substitute it back into our equation, and this gives us am squared e to the x plus bm e to the x plus c times e to the x is equal to 0. We can factor out the e to the x, and we're left with what's called the auxiliary or characteristic equation, am squared plus bm plus c is equal to 0. We can solve this equation for m by using the quadratic formula, and we get minus b plus or minus the square root of b squared minus 4ac all divided by 2a. The type of roots for this equation depend on what's inside the square root, b squared minus 4ac, and that's called the discriminant. There are three different types of roots that we can get to this equation. The first type is when b squared minus 4ac is greater than 0. When that happens, we're going to get two distinct real roots, and we're going to call them m1 and m2. The solution to the differential equation is then y is equal to c1e to the m1x plus c2e to the m2x. The second type of roots that we can have is when the discriminant b squared minus 4ac is equal to 0. When this happens, we are going to get one repeated root, and the solution to the differential equation is going to be y is equal to c1e to the mx plus c2 times x e to the mx. So the exponential looks the same. The second part just has an x included with it. The third type of root that we can have is when the discriminant is less than 0. When this happens, we have a negative inside the square root, and that gives us two complex conjugate roots, and we're going to call them m is equal to alpha plus or minus I times beta. The solution is a little bit more complicated, and it's y is equal to e to the alpha x, and then that multiplies c1 cosine beta x plus c2 sine beta x. Before we dive into some example problems, let's briefly go over the steps that you can follow for solving any homogeneous linear constant coefficient equation. To solve an equation that is second order and looks like ay double prime plus by prime plus cy is equal to 0, there's two steps that you can follow. The first is to solve the characteristic equation. Remember, that just comes from setting y equal to e to the mx. And then the second step is to choose the appropriate form of the solution. And the form is going to depend on if you have two real distinct roots, one real repeated root, or two complex conjugate roots. The other type of homogeneous linear constant coefficient equation that you might be asked to solve is a higher order one. And I've just written down the general form for that right here. The steps are going to be pretty similar to the ones that we just looked at for solving a second order equation. The first step is to substitute y is equal to e to the mx into the equation. In step 2, you're going to solve the resulting equation for m. And then in step 3, you're going to write the general solution, and you're going to base the general solution on the types of roots that you have for m. We'll walk through some examples so you can see exactly how that works. we're going to walk through 3 examples where we're going to solve a second-order homogeneous linear differential equation. To make things easier, I've written down the general form for this equation over here on the right, and I've also written down the 2 steps that we can follow. Let's look at our first example. It is y double prime minus y prime minus 6y is equal to 0. In step 1, we want to write down the characteristic equation and then solve it. For this problem, the characteristic equation is m squared, that's because we have 2 derivatives, minus m minus 6 is equal to 0. We can factor this as m plus 2 times m minus 3, set that equal to 0, and this gives us m is equal to minus 2, and then m is equal to 3. For this problem, we have 2 distinct roots. And let's call these roots m1 and m2. The general form for our solution is going to look like y is equal to c1e to the m1x plus c2e to the m2x. Our solution then is y is equal to c1e to the minus 2x plus c2e to the 3x. And that's all there is to it. Let's now look at our second example. We have y double prime minus 10y prime plus 25y is equal to 0. Let's begin by writing down the characteristic equation. That's m squared minus 10m plus 25 is equal to 0. Let's factor it. We have m minus 5 and another m minus 5, and that's equal to 0. This gives us m is equal to 5 and 5. So we have what's called 2 repeated roots. For step 2, let's start by writing down the general form for our solution. Because we have 2 repeated roots, the general solution is going to look like this. Y is equal to c1e to the mx plus c2 times x e to the mx. Our solution then is y is equal to c1e to the 5x plus c2 times x e to the 5x. You could factor out the e to the 5x, but you don't need to. I'm just going to leave our solution just like that. Let's now look at our third example. We have y double prime minus 6y prime plus 13y is equal to 0. Since we have 3 forms of a solution and we have 3 examples, you can probably guess that this one is going to give us complex roots. Let's see. Our characteristic equation is m squared minus 6m plus 13 is equal to 0. Let's now factor this. We definitely need to use the quadratic formula. So m is going to be negative b, so that's minus a minus 6, plus or minus the square root of b squared, that's minus 6 squared, minus 4 times a, which is 1, times c, which is 13. And all of this gets divided by 2 times a, which is 1. Let's see. This gives us m is equal to 6 plus or minus the square root of 36 minus 52. And let's divide all of this by 2. This is equal to 6 plus or minus the square root of 36 minus 52. Let's see. That is minus 16. And we divide it by 2. So this gives us 3 plus or minus the square root of minus 16. Let's see. Let's write down that the square root of minus 16 is 4 square root of minus 1, which gives us 4i. So we have 3 plus or minus 4i divided by 2, so that gives us 2i. And these are what we call two complex roots. Our solution in step 2 is going to look like this. Y is equal to e to the alpha x times c1 cosine of beta x plus c2 times sine of beta x. Now let's think about alpha and beta. Alpha is the real part of our complex number, and then beta is the imaginary part. This gives us y is equal to e to the 3x times c1 cosine 2x plus c2 sine of 2x. And there's our solution. Let's now walk through two examples where we're going to solve a second-order homogeneous initial value problem and boundary value problem. The general form of the equation is over here on the right. ay double prime plus by prime plus cy is equal to 0. And I've also included in purple the 3 steps that we're going to follow. Let's look at our first example. It is y double prime plus 16y is equal to 0. And we're given the initial conditions. Y of 0 is equal to 2, and y prime of 0 is equal to minus 1. You could think of that as the initial displacement and the initial velocity. Our first step is to write the characteristic equation and solve it. The characteristic equation is m squared, that comes from the two derivatives, plus 16 is equal to 0. This gives m squared is equal to minus 16. This gives us m is equal to the square root of minus 16, which is equal to plus or minus 4i. I think it's helpful if we think of this as 0 plus or minus 4i, so that we can remind ourselves that 0 is the real part and 4 is the imaginary part. In step 2, we are going to choose the appropriate form of our solution. Because we have complex roots, our solution is going to look like y is equal to e to the alpha x times c1 cosine beta x plus c2 sine beta x. Our alpha is equal to 0 and our beta is equal to 4. So our solution is y is equal to e to the 0 times x times c1 cosine 4x plus c2 times sine 4x. This gives us y is equal to e to the 0, which is just 1. So we have c1 cosine 4x plus c2 times sine 4x. Our third step is to use the conditions that we've been given to find c1 and c2. Let's start with the condition that y at 0 is equal to 2. This means that we're going to substitute in that x is 0 and y is 2. Looking right here, this gives us 2 is equal to c1 times cosine of 0 plus c2 times sine of 0. Cosine of 0 is 1, so we have 2 is equal to c1, and then sine of 0 is 0, so we just have c1 is equal to 2. I think it's helpful after you find one constant to go ahead and plug it back into your equation. So our equation now is y is equal to 2 cosine 4x plus c2 times sine 4x. Let's now look at our second condition. Let's go back up. It is right here. Y prime of 0 is equal to minus 1. What we're going to have to do is take the derivative, and that is going to be 2 times the derivative of cosine, which is minus sine 4x, times the derivative of what's inside, which is 4, plus c2 times the derivative of sine, which is cosine, of 4x, times the derivative of what's inside, which is 4. Let's now substitute in, from our initial condition, y prime of 0 is equal to negative 1, that x is equal to 0, and y prime is negative 1. On the left, we have negative 1, and then we have a minus 8 sine of 0 plus 4c2 cosine of 0. Sine of 0 is 0, so we just have minus 1 is equal to 4 times c2. This gives us that c2 is equal to minus 1/4. We can now write down our solution. It's y, and I'm looking right here, is equal to 2 cosine 4x minus 1/4 times sine of 4x. And let's highlight that. This solution is called a sinusoidal function, and I've graphed it over here on the right. You can see that when x is 0, y is equal to 2, and then the slope at 0 is equal to negative 1. So our solution matches up with the initial conditions that we've been given. Let's now look at our second example. It is y double prime plus 8y prime plus 16y is equal to 0. And our boundary conditions are y of 0 is equal to 1 and y of 1 is equal to 0. Our first step is to write down the characteristic equation, and that is m squared plus 8m plus 16 is equal to 0. We can factor this as m plus 4 times m plus 4, and that's equal to 0. So we get that m is a repeated root minus 4 and minus 4. Our second step is to write down the solution based on the fact that we have 2 repeated roots. Our solution is y is equal to c1e to the mx plus c2 times x e to the mx. You just multiply by x when you have a repeated root. For our problem, the solution then is y is equal to c1e to the minus 4x plus c2 times x e to the minus 4x. In step 3, what we're going to do is we're going to find c1 and c2 using our boundary conditions. Let's use the first condition that y of 0 is equal to 1. So that tells us that x is equal to 0 and y is equal to 1. Let's plug that in. We get 1 is equal to c1 e to the 0 plus c2 times 0 times e to the 0. So this is nice. This just means that c1 is equal to 1. Let me highlight that. And let's go ahead and let's plug that into our equation. So we have y is equal to 1 times e to the minus 4x plus c2 times x e to the minus 4x. Now we're going to use our second boundary condition, and that is y at 1 is equal to 0. So this tells us that x is equal to 1 and y is equal to 0. Let's plug that in. We get 0 is equal to e to the minus 4 plus c2 times 1 times e to the minus 4. This gives us that C2 times e to the minus 4 is equal to minus e to the minus 4, which tells us that C2 is equal to minus 1. Now we can write down the general form of our solution. Here's the form with the constants, and now we're going to plug in those constants, and we get y is equal to C1, which is 1, so we just have e to the minus 4x, and then we have a C2, which is minus 1, so that gives us minus x e to the minus 4x. And let's go ahead and let's pull out an e to the minus 4x. So we have 1 minus x times e to the minus 4x. And that's our final solution. This solution is a decaying exponential function, and I've graphed it over here on the left. And you can see that the solution passes through the boundary points. Y of 0 is equal to 1, and y of 1 is equal to 0. Let's now look at two examples where we're going to solve a higher order homogeneous linear differential equation. To make things easier, I've written down the general form of a higher order equation. Don't worry, it's not nearly as bad as it looks. And then I've also written down 3 steps that we can follow for solving an equation like this. Let's look at our first example. We have y triple prime minus 4y double prime minus 5y prime is equal to 0. The first thing that we want to do is substitute in that y is equal to e to the mx. For this type of equation, this is what our solution looks like. Substituting this in, we end up with m cubed e to the mx. That's because we have 3 derivatives, minus 4m squared e to the mx, minus 5m e to the mx is equal to 0. This gives us m cubed minus 4m squared minus 5m times e to the mx is equal to 0. And this gives us then that the only way it's going to be 0 is that if m cubed minus 4m squared minus 5m is equal to 0, because remember, an exponential is never equal to 0. In step 2, we are going to solve this equation. Notice that we can pull out an m, so let's do that. We have m times m squared minus 4m minus 5 is equal to 0. Let's factor this. This factors as m minus 5 and m plus 1. And this gives us that m is equal to 0, 5, and minus 1. So we have 3 distinct real roots. In step 3, we need to write down the general solution based on the fact that we have 3 distinct real roots. Our solution is going to be y is equal to c1 times e to the first m, which is 0 times x, plus c2 times e to the 5x, plus c3 times e to the minus x. This gives our general solution is y is equal to c1, because e to the 0 is 1, plus c2 e to the 5x, plus c3 e to the minus x. And there's our solution. Let's now look at our second example. This one's a little bit more complicated, but it's not too bad. We have the fourth derivative of y plus y triple prime plus y double prime is equal to 0. Let's begin by writing down our characteristic equation. I think after doing the first example, you can see that the e to the mx is going to go away. So we can just write down the characteristic equation, which is m to the fourth plus m cubed plus m squared is equal to 0. Now in step 2, we're going to solve this equation. We can factor out an m squared, and that leaves us with m squared plus m plus 1 is equal to 0. The m squared is going to give us that m is equal to 0 and 0. And then for this one, we are going to have to use the quadratic formula. Our solution is m is equal to negative b, which is minus 1, plus or minus the square root, b squared, which is 1 squared, minus 4 times a is 1, and then c is 1, all divided by 2 times a, which is 1. So let's see. This is m is equal to minus 1, plus or minus the square root, 1 minus 4, so that's minus 3, all divided by 2. So this is minus 1/2 plus or minus the square root of 3 over 2 times I, because of the negative inside the square root. Before we write down the solution, let's write down what type of roots we have. Over here on the left, we have 2 repeated roots. And then over here on the right, we have 2 complex roots. Our solution is going to look like this. We're going to have y is equal to c1 times e to the 0 times x. That's our first repeated root. Plus c2 times x times e to the 0x. That's for our second repeated root. And then with our complex roots, we're going to have e to the real part, which is minus 1/2. So we have minus x over 2. And now we have to take into account the complex part, which is the plus or minus root 3 over 2. So this gives us c3 times cosine square root of 3 over 2 times x plus c4 times sine square root of 3 over 2 times x. We can then rewrite our solution as y is equal to c1 plus c2 times x. That's because e to the 0 is 1. And then we're just going to recopy this last part. E to the minus x times c3 cosine root 3 over 2 times x plus c4 times sine root 3 over 2 times x. And there's our solution. And that's it. You now know how to solve homogeneous linear differential equations with constant coefficients by forming the characteristic equation, identifying the types of roots, and then writing the appropriate general solution. You should now be ready to work through additional practice problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.